Alright, here's a problem from Chapter 5, dealing with circular motion. Consider a vehicle traveling at a constant speed, making a turn around a curve on a flat road with radius r. Since the vehicle is traveling at constant speed, the magnitude of momentum is the same everywhere, but the direction of momentum is changing, as given here. Now let's begin this problem by applying the momentum principle, which is F equals dp dt. Then we can factor momentum into the product of the magnitude of momentum times the unit vector in the direction of momentum. So taking the derivative of this form of momentum yields this result. This value here is the rate of change of the magnitude of momentum, and this is the rate of change of the direction of momentum. Now, since we talked about the magnitude of momentum is not changing since the speed is constant, this whole value is going to be 0, so I crossed it out because that whole thing is going to go to 0. Now, the direction is changing, and it's always perpendicular to the direction of momentum, so the force is going to point towards the center of the circle, as given by these F bars things. So we have F equals the magnitude of momentum dp hat over dt. And if we take the magnitude of dp hat over dt, that actually equals the magnitude of velocity over the radius. So we can put that into our formula for force, and we get the magnitude of momentum times the magnitude of velocity over r. And we know that momentum is roughly mv. So plugging in that, we get m magnitude of velocity squared all over r, and that's actually the perpendicular force. Now, the main question at hand is to determine the fastest speed the vehicle can go and make the turn. So, if we want to know the fastest speed that the vehicle can go to make the turn, we need to set this equal to the frictional force. And this is going to be the maximum frictional force for the fact that we want to determine the fastest speed the vehicle can go. So let me rewrite that last equation at the top here. So we have the frictional force, and that's the static frictional force, our maximum static frictional force, and that equals mv squared over r. Now this is equal to mu s times the normal force equals mv squared over r, and the normal force is going to be equal to mg, the gravitational force. Notice that the masses cancel, so this problem doesn't even depend on the masses. And it says we're looking for the fastest speed the vehicle can go. Again, we're solving for v. So when you algebraically do that, you get the square root of r mu s, which is coefficient of static friction, times g. And if we say, because we want to plug in some numbers just to see, because everyone likes numbers, let's say r is 75 meters and the coefficient of static friction is 0.25, and we know that g is 9.8 meters per second squared. So plugging in that, we get the square root of 75 times 0.25 times 9.8, and I checked, the units do come out to be meters per second, so that's good, and this value is 13.6 meters per second after plugging all that into a calculator. And now let's change the problem slightly. Let's say you want to go 20 meters per second, that's what speed you want to go. But the vehicle will not be able to make the turn because it's traveling too fast. The force of the road cannot exert enough force on the vehicle to keep it moving in a circle. So let's solve for the coefficient of static friction that will allow for you to travel at this top speed. So again, we have mu mg. Once again, the masses are going to cancel, as you're going to see here. Masses cancel, and let's solve for mu s. And that's just going to be v squared over rg, and plug in that 20 meters per second squared, which is going to be meters squared over second squared over 75 meters, and our 9.8 meters per second squared. And notice that all these units are going to cancel out, which is good because the coefficient of static friction doesn't have any units. And when you do this computation on a calculator should get 0.544. And that answers all the parts that I was willing to answer, and that concludes this problem. Thank you.